So we can start by writing the data. For the still tank, the weight for the mass for the still tank is 5 kg, and that of water is 40 kg, and that of the still casting was 2 kg. The specific heat capacity for still tank was 0.5 kg, that of water 4.18 kilojoule. Look at the question. Same 40 kg of water initially at 25 degrees Celsius is contained in a perfectly insulated still tank. That means the water was contained in a still tank. That means it implies they have attained the same equilibrium, thereby they'll be having the same temperature. So we are not given any information on the temperature of the water of the still tank, but rather on the water. But since the water is in the tank and they have attained the same thermal equilibrium, that means they are going to have the same temperature. So if the temperature of the water was 25 degrees Celsius, then that of the still tank will also be 25 degrees Celsius. Here we are just given the specific heat capacity of the still, but we know the still tank and the still casting, they are all made of steel. That means they are going to have the same specific heat capacity. We are not given the final temperature of any of them. So now how do you go about this? In insulated, that means it's what? It's an adiabatic process, or the boundaries are adiabatic. That means there will be no transfer of heat between the system and the surrounding, because the boundary is not dithermal. So here when you say this, you say the still casting is having a higher temperature value compared to the still tank and the water. That means from the second law of thermodynamics, heat will always flow from higher value to a lower value. So here the still casting is very hot, so heat will always flow from a hotter body to a colder body. So the heat that will be lost by the still casting will be gained by the still tank and the water, and after some time they are all going to attain the same thermal equilibrium and they will be having the same temperature. So we can write our equation: heat gained by water in still tank will be equal to heat lost by the still casting. So heat gained by the still tank, I'm representing with the QS, and heat gained by the water KW, and heat lost by the still tank. So I write my equation, the next one, then I substitute in the value. So then the rest is just math. I divided through by 1000 just to make the numbers very small and not huge. Imagine you're multiplying 40 times 4.18 times 1000 times 20. That's going to be a very big one. That's why I decided to divide through by 1000. So you can choose to leave yours like that. And the next one, just group in like times 0.5 plus this. Then I arrive at this. Someone will say you should be thinking of converting the change in the temperature to Kelvin before using. When you do same, you are going to get the same answer, because when you are dealing with conversions of temperature and it's involving multiplication, when it is involving multiplication, you can choose not to convert them, because change in Kelvin is the same as change in degrees Celsius, because they all have the same temperature difference of 100. The difference between the lower point of degrees Celsius and the higher point is 100. They have equal spacing, but we can say the same for Fahrenheit. So when it's between Kelvin or degree, you can just leave it like that and use it for your work, and you arrive at the same solution.